Welcome to Drone System and Control course. Today we are going to talk about autopilot design further. The previous lecture we talked about system architecture, functional requirement. In this we will talk about different modes of flight, control system architecture, understanding and control allocation aspect of it. Right? It's a continuation with respect to previous lecture. Now different modes of flight. We talked about stabilized mode, altitude mode, position mode and trajectory mode. To recollect, in stabilized mode you have a basic modes of, it's a very basic mode of flight. Pilot is responsible for controlling the drone. The autopilot only stabilize the drone, which means maintain only attitude of the drone. The RC stick controls the pitch roll yaw. If you leave the stick, the drone will level automatically, right? Stabilize automatically. The thrust command directly sent to control allocation. 50% in stick will maintain the altitude. Less than that will start descending. Horizontal position and heading or drift due to wind conditions, right? So pilot have to correct it automatically. He wants a position to be there, he has to correct the position based on the RC. Now when we move on to altitude hold mode, right, we talk about maintaining altitude and basic stability of the drone. A pilot is responsible for controlling the drone. Basically the stick control will give a pitch roll yaw command. Levels automatically if the pilot leaves the stick. Thrust command controls the vertical velocity rather than the direct thrust, it will just control the velocity. Horizontal position and heading will drift due to wind condition. The pilot have to use the stick to correct. Right? Pilot controls altitude too. Now this is lesser load when compared to stability mode. Position mode or loiter mode, autopilot maintains altitude, horizontal position, heading and basic stability. Autopilots take over more responsibility and reduces the workload on the remote control pilot. Right? It levels automatically and holds its position, holds heading, altitude if the pilot leaves the stick. Right? If the pilot gives a velocity command, it will just respond to it. If he leaves the stick, it hold position, altitude and heading. Suitable for aerial photography kind of applications. No drift in horizontal position, heading or altitude when subjected to wind condition. The autopilot will automatically correct the altitude and attitude and hold the position in global frame of references. Right? So here again 50% stick, maintain the pitch roll, yaw, attitude and altitude of the drone. There is another mode called trajectory mode or mission mode. It is more of autonomous mode. Again the workload on the pilot will decrease significantly when you move from stabilized mode all the way to higher modes, right? The trajectory mode. Follow predefined path automatically, right? Autopilot maintains altitude, heading, orientation, horizontal position to follow the trajectory. Lesser workload on the pilot, right? Most of the work is done by the autopilot itself, right? It follows point A to point B at a specific velocity. And if you say this is altitude it maintains the altitude while following the path automatically. These kind of modes are suitable for surveying, mapping or payload delivery. So as I mentioned earlier, if you just give a box, right, this is my field and I want to survey this particular field in a land mover pattern, right, and then you want to do this, it's a predefined path. Autopilot will do automatically this predefined path, right. That's the advantage in the trajectory mode. It follows the trajectory provided by the pilot, right. The ground control system sends the predefined path and with a timestamp to the autopilot, right. What time you want to be at what position, right. That will define the velocity at which you want to go from point A to point B. what is the rate of turn that you are looking for. All that will be given from the ground station, and that will be loaded in Autopilot, and Autopilot just simply follow the command and takes care of necessary position correction, altitude correction and heading corrections. Right? Functional, safety, performance requirements helps in defining Autopilot system architecture. Right? We need to look at functional aspect of it, we need to look at the safety aspect of it, we need to look at the performance requirement. If you say you want to go to specific altitude, what is that altitude position could be, error acceptable to you, right? All that performance requirements will also defines the Autopilot system architecture, right? Now let's try to understand the functional requirements in advanced modes. There are modes, these are the basic modes, there are some advanced modes, right? Hold mode, you just want the drone to hold its position, right? Vehicle stop wherever it is, hover at the current position and altitude, right? Suppose you lost the communication and you wanted to check whether you can re-establish the communication. You can just write, if communication is lost, you hold and the position itself till you establish your communication, right? You can do that. This is hold mode. Return mode, vehicle return to safe altitude and hold, right? Suppose I am flying at a higher altitude, something happened, I can say return mode, return to the safe altitude and stay, or return to safe starting location, you can do that. Return to what? You can define, this is the mode, right? You can define those kind of modes which is more for safety aspects of it, right? And which can be triggered based on certain sensor failure or certain communication loss. You can execute these maneuvers. These are more advanced, predefined, right? Takeoff mode. Takeoff mode means it just predefined speed at which it takes off from the ground, go to some altitude h and stays there, right? That's your takeoff mode. Landing mode also can be enabled. It's like vehicle automatically land to predefined speed from particular altitude to the ground. You don't have to set this information, it is predefined based on system characteristics. One can just define this and preload those informations. That will be useful for operators many a time, right? You can also have orbit mode. Orbit is basically you just want to go around, you want to monitor one particular region. It just goes around in a circle with a fixed radius and heading. You can say clockwise or anti-clockwise, it just goes around that particular point, right? You can have a constant monitoring that particular region, that is possible, right? Follow mode, you can have a transmitter which keeps sending the position of it, and that position will be followed by the drone automatically. If you are looking at a convoy protection kind of a scenario, convoy is moving at a specific speed and at location, it transmits the speed and location automatically to the drone and it can just follow those position automatically. Or you can have a camera, the camera locks on to the target and target speed and heading is estimated from there and just follows the target, right? That is the mode. These are like what we define, predefined advanced modes one can just define, and this can be used based on whatever the mission you are performing, right? Off-board mode. The autopilot takes command from a companion computer. If you are talking a fully autonomous system, right? Your companion computer is going to make all the decisions, not the pilot. Then you get into off-board mode, right? I am talking from Pixoc or Autopilot architecture, right? If you are talking about it, my flight controller will not make the decision, right? It not talk to the operator, it just talk to the companion computer. The companion computer will just tell the pilot or autopilot to do what it is expected from the drone, okay? These are some advanced modes. Many advanced modes can be defined based on the requirements. For the basic modes are whatever you get the stability, right? Altitude hold, position hold and trajectory tracking. These are the basic automatic control system we define, and that's present in our autopilot, right? This is mostly suitable for semi-autonomous mode, right? Semi-autonomous operations, right? Where the workload on RC pilot decreases when you go from lower mode to higher mode. Okay, let's try to understand the flight control system architecture, how it has been, how it's structured, right? So we have a basic thing which is your motor command system. The motor command system will give an RPM command, PWM command, which goes to your electronic speed controller unit, and that ESC will produce necessary voltage, and that will result in change in RPM in your motor. That's your system, right? Motor command system gets an input from flight management system. We'll talk about individual aspects of what are these and then in subsequent slides. Flight management system, suddenly you see a drone is operating very close to a target. It is dangerous, right? You want to disable it. You can just send a command directly to a motor and just disarm the motor, which basically you are off, turn off your motor or turn on your motor. It's a remote on and off switch, right? Arming and disarming. Till you arm, any command from the flight controller will not go through, right? You disarm, even if your system's sensors are functioning, no input will pass the motor command system. Basically, here the output is always 0, right? So RC can just directly send the arm disarm signal, or GCS can send the arm disarm signal to your motor command system. Then comes your control allocation system. Based on the architecture, based on the frame, how the physical system is produced, the control allocation system produces a motor commands, and the motor command will be passed to the motor command system to produce PWM output. Then comes your flight control system. It takes input from RC or input from GCS. The flight management system will tell you what mode in which you need to operate. Based on the modes of flight, the respective control architecture will be triggered, and that will be executed here. The gains for different modes of flight will be available here. The flight controller provides output like a thrust. What is my thrust command? What is my roll, pitch, yaw commands? It will be providing to your control allocation system, right? Flight management gives you modes of flight, basic modes of flight that goes as an input to your flight controller. Now, I have a sensor which is measuring all these states of the system like IMU, GPS, barometer, or optical flow sensor, or your altimeters. It could be a LiDAR or radar. All those sensors comes in. You have a state estimation. That estimator gets the states of the system. The estimated states sent to your flight control system. Estimated state is also needed for flight management, right? If I see a GPS, loss of GPS signal, right? I don't see a GPS input. The sensor along with the states of the sensor will come in, and that will go into your flight management system. You don't have to estimate that particular state, but you can just do that, right? And suppose your flight management system not just only looking at, let's say you want a velocity of 3 meter per second, but your current velocity is 4 meter per second. It goes directly and it pass on to it. Suppose you defined a geofence, you have to be within a square of 1 square kilometer. Your current position is not within that, it's just outside. It goes to the flight management system. The flight management system will decide what it has to perform when you are outside the safe boundary, right? So those inputs also goes to flight management system, right? The flight management system basic requirement is it takes care of the safety of this whole drone, right? It perform high level decisions, right? It talks about what kind of modes in which the flight controller should operate. It also provides the interface between the ground control system and remote pilot, right? It also takes decisions like operator based decisions. Basically, operator wants to change the mode of flight from automatic to manual, flight management system will take care of it, or sensor based decision. Suddenly is that I lost signal, I want to go return to home, or I cross the geofence, then I have to take action based on that, or I'm just seeing something that I want to land, loss of communication, I wanted to land wherever I am. So all this decision will take place in flight management system, right? Now let's get into understanding of flight control system, right? What flight control system going to do? That's a very important module, right? That's where we are going to design a controller and just going to implement the controller game, right? Flight control system provides pitch command, roll, yaw and throttle command. What is the input to it? RC input, right? What the pilot is giving us a command. If it's not pilot is giving a command, the flight management system will give you the command, right? What is the waypoints that is being loaded? That waypoints will come into picture. The flight modes will come into picture. If there is a reset, mode reset, I am changing suddenly from stabilized mode to position hold mode, and all the mode reset or change will come to flight control system, right? Flight control system also receives estimated states from your sensor fusion, right? Flight mode changes the nature of the command to the flight control system. What is the command input going to be, right? Stick is either is a position, velocity, pitch, roll, rate, yaw rate, or what is that its command going to be, right? That switch is also going to take place. In stabilized mode, stick command, attitude, throttle directly, right? So that will go into control allocation directly. In altitude mode, stick command, attitude, throttle command converted into climb or descend, right? It's a vertical velocity, if a positive or negative, right? That's what will happen to your throttle command at that time. In a position command, yaw stick command attitude, whereas pitch, roll, thrust commands velocity, right? In trajectory mode, you have XY, yaw and Z information, right? Now let's get into details of flight control system architecture, right? We saw this in the previous lecture, right? But let's dwell in much more details to it, right? Drone, it flies, the multi-rotor flies, and the sensors are connected to it. The sensor will provide the current state, whatever the measurable states, pass on to your fusion module. Your fusion module estimate, right? Then there is a safety command goes into a control allocation, and you also get direct thrust command comes into control allocation. The control allocation will provide desired RPM, and that will go into your motors, right? Electronic speed control units, and which controls the motor, right? The sensor will provide attitude to attitude controller. The attitude controller will give you desired moments required, pitch, roll, yaw, moment required, right? Thrust comes directly from your position command, right? That's the inner loop. If you change the mode from stability mode to position mode or altitude mode or the tracking mode, then your position velocity controllers comes into picture. They take input directly from the user based on the previous slide what I mentioned. For a different mode of flight, the pilot stick has a different meaning to it. That meaning will be sent directly here, and those control architecture comes into picture, and they provide necessary outer loop commands to the system. The inner stability is always taken care, right? Now let's understand control allocation a little bit. Control allocation is a process of distributing desired control input, basically your forces and moments, into individual actuators, right? Like motors, or it could be a control surface. If we talk about a fixed wing aircraft, we are just talking about control surface deflections, right? That's what your control allocation is all about, right? You have two surfaces. How much you want both of them to deflect? You want them to deflect equally or differentially, right? That decision is what control allocation is all about. In case of multi-rotor system, it's all about the motors, right? it takes care of the physical and structural constraints, right? It is a final stage in the control loop. Afterward, it just sends commands directly to the actuator, and actuator performs the necessary action onto the physical system, and you see observations through your sensors. Takes a desired collective thrust force and moments above the body axis and from the controller. It could be PID or it could be LQR, your MPC, which is sitting in your inner loop attitude controller or outer loop. It takes all this information, and what you get this, right? It computes the individual actuator command. It depends on how the configuration is, right? How your multi-rotor system are configured. It's a plus configuration or a cross configuration in a quadcopter or in hexacopter, how it has been arranged. Is there any tilt in the structural position? It takes care of all the informations and compute the control input. It also ensures the constraints. The constraints are basically what's the limits. If you are commanding some RPM which is greater than what is possible, it just provides a saturation, U min and U max, right? A minimum RPM to maximum RPM, right? It also takes care of the power bounds. What is the maximum power that we can expect, right? So it also take care of all those aspects of it in the control allocation module. Now, let's try to understand what this control allocation module does. We call this as a kill switch command. If you remember, when I talk about flight control system architecture, there is something called arm and disarm. Arm, basically before starting the vehicle, the user have to say, now the system is ready. Then you are allowing a control allocation module to function, right? Basically it's turning on your control allocation module. Anytime you can disarm, right? You can say, that's it, I don't want the control allocation module, I can disarm. Basically I can turn on off. So it's a soft on off switch, right? Then you have a desired thrust and desired moments coming from your attitude, and that's passing to your control allocation to produce desired RPM commands. So differential thrust techniques are used to generate a desired moments, right? So what is the our flight controller, what we are going to see in the next lecture. The flight controller will produce U1, U2, U3, U4. Basically desired thrust, pitch roll, yaw and desired thrust, right? So we know that the motors, in the beginning of the course we talked about the dynamics of the drone, where we talked about how the drones are, how the thrust has been connected, and thrust and torque from individual motors produced based on the configuration, how we can express the control input in terms of the thrust. U1 is basically T4 minus T2, T4 is this minus T2, right? This and the length is the length of the arm, that talks about the pitch. U2 is T1 and T3, let's talk about roll. U3 is your yaw, this basically coming from the torque of all the 4 motors, right? Because 2 of them rotate in one direction, the other 2 rotate in opposite direction, that's how it been U3 comes out. U4 is total thrust, T1 plus T2 plus T3 plus T4, that's your thrust, right? Now let's look at how the control allocation matrix for a quadcopter, right? So based on the length of the arm, right, and previous U1, U2, U3 equation, I can write U1, U2, U3, U4, that's my required thrust and moments coming from my stability loop, as well as the command directly in stabilized mode or in other modes. Basically the controller will estimate these values, right? What is a control input required? But that has to be translated into thrust T1, T2, T3, T4, desired thrust what we are looking for, right? Now I am just converting this previous equation representing in a matrix form, right? Here thrust and torque have a quadratic relationship with respect to RPM, because I don't want thrust, because I can't command thrust directly to my motor, but I have done the test in a thrust bench. I did the test, I calculated what is the thrust from a specific motor propeller for an RPM. I have this data, right. Using this data, I can find out what is the relationship between thrust and RPM. I can find out the K, right. So I can substitute, that's your K, and then I can also get the similar to thrust. I can also plot torque versus RPM from a thrust bench, and I can collect the data. We talked about all this when we talked about modeling of multi-rotor system. I can get the value Q, right. So I can normalize to a single quantity, what we call C, which is Q by K, right. So with that I can represent U1, U2, U3, U4 to omega 1, omega 2, omega 3, omega 4, basically RPM commands, which goes directly to electronic speed control unit, right, and this is the matrix. But what actually we need omega 1, omega 2, omega 3, omega 4 for a given U1, U2, U3, U4, which means I need to, so I have to find out what is my omega matrix vector, which will be inverse of this matrix. Let us say this control allocation matrix we are talking of, A inverse, right, U, that is my omega, right. Here it is a 4 cross 4 matrix, I can invert, right. Suppose we go into a hexacopter, based on the configuration this control allocation matrix will differ, right. I am trying to normalize again, L is the arm length, kappa is the propeller torque coefficient, and mu is the propeller thrust coefficient, and using those informations I am going to write about what are the RPM required. What actually we need omega with respect to, let us say this is control allocation matrix A, I want an inverse of this. Now A matrix dimension, if you see, it is 4 cross 6, it is a rectangular matrix. I can't get direct inverse, I may have to do a pseudo inverse times U, then I can get my omega, right. So for quadcopter, RPM command can be directly computed from the inverse of the control allocation, whereas a multi-rotor more than 4, one use pseudo inverse to compute RPM, right. Again for octocopter it differ based on the configuration. I am not going in for various configuration how the control allocation matrix, if it is a plus configuration, a cross configuration, the control allocation matrix will be different, and even in quadcopter, right. You may have the angle, your length is not, your arm may not be just parallel to this surface, it may be slightly inclined. In that case you have to resolve them into two components, right. So those things will come into picture. I am not talking about all of this, it is beyond the scope of the particular lecture. Those who are interested in, they have to study, right, those aspects. We will provide an additional reading material for those configurations, okay. But one need to remember, based on the physical system, the control allocation matrix will be different, and one need to relate the command RPM versus control input generated from flight control system, right. This U1, U2, U3, these are generated from flight control system, okay. Based on the requirement, these are generated, this is my command to actuate, right, basically my motor to generate necessary RPM, okay. In a summary, we understand the overall system architecture, understand the functional requirement of the autopilot, we understand the software structure in flight control system. We looked at the ground control station. We looked at the software structure in the autopilot, the brain, where it has a driver, it has a middleware, it has an storage logging mechanisms. We looked at the hardware, how the hardwares are connected when you are operating in a normal mode or you are operating in a stability mode, how the hardwares are connected. We understood the control architecture for inner loop and outer loop, and we focus mainly on control allocation matrix in this lecture, right? How U1, U2, U3, U4 generated from different modes of flight, right, converted into RPM command. See, one message here is based on the system, the control allocation matrix will differ. One need to understand that, right? Once you have, you can transform U1, U2, U3, U4 to respective RPM commands. Thank you.